Okay, we're going to be starting worksheet 4.5, and I want to start out by looking over our notes. So pull your notes out and make sure you have your highlighter and a pen so that you're able to mark your notes. And you're going to also want to make sure that you have worksheet 4.5 so that you can fill that in later on. And it's a good idea to also have your textbook in front of you as well. Alright, so let's go over this together. Chapter 4.5 is entitled Concentration of Solutions. And when we're talking about concentration of solutions, we're talking about the behavior of solutions often depend not only on the nature of the solutes, but also on their concentrations. Okay, so the behavior, we're looking at the behavior in solutions, and it's not just about what the solute is, the nature of the solute, but also we need to consider concentration. The definition for concentration, you're going to want to highlight this and study it. The definition is the amount of solute dissolved in any given quantity of solvent or quantity of solution. Concentration is intuitive. The higher the amount of solute dissolved in a certain amount of solvent, the more concentrated the solution. Okay, so you're going to want to stop for a second and think about that for a minute. Concentration being intuitive. The higher the amount of solute dissolved in the solvent, the more concentrated the solution. You have to be able to express concentration of solutions quantitatively. What does that mean? That means that this whole section is going to be a lot of math work. Okay, when we're figuring this out, we have to deal with a term called molarity. Molarity expresses the concentration of a solution as the number of moles of solution in a liter of solution. So yes, there's a formula for that you're going to have to work with. Molarity equals moles of solute over volume of solution, and this is very important that you remember it's in liters. A 1 molar solution, which is written just like this, it's a capital M, 1.00 capital M, contains 1 mole of solute in every liter of solution. So I just verbalized right here what I just said right here as far, this is the formula expression and this is the verbal expression. So if you look at figure 416 on page 146, it will show you a procedure for preparation of 0.250 liters of a 1 molar solution of copper sulfate. So what they do is they weigh out 0.25 moles of copper sulfate, which if you do the stoichiometry, it turns out to be 39.9 grams because the formula weight of copper sulfate is 159.6 AMU. B, right here, you're going to put the copper sulfate, the solute, copper sulfate, into a 250 milliliter volumetric flask. This is the volumetric flask. And you're going to add a small quantity of water. And then C, you're going to dissolve the solute by swirling the flask. And then D, you're going to add more water until the solution just reaches the calibration mark etched on the neck of the flask. Shake the stoppered flask to ensure complete mixing. Okay, so I wanted to show you exactly how that's done in a lab. Now, how do you prepare 250 mils of a 1 molar solution of copper sulfate? And I just read it to you, but this is the math behind it. You had to figure out how many grams is 0.250 moles of copper sulfate. And we already said that copper sulfate has a formula weight of 159.6 AMU. Okay, so we take the weight of copper, the weight of sulfur, and the weight of the 4 oxygens, you add them together and you get 159. And then if you do the stoichiometry, you know that 0.250 moles of copper sulfate, if you do dimensional analysis, if you cross out, you put the 1 mole of copper sulfate in the denominator, 0.250, that's in the numerator, opposite sides cancel. So 0.250 times 159.6 grams, it will come out to be 39.9 grams of copper sulfate. This is a solid. Okay, then you're going to weigh it out, and you're going to place it in the volumetric flask that's calibrated to hold 250 mils. And you're going to plug into the equation that we just did up here, this equation, molarity, the 0.250 moles of copper sulfate is the solute, and you're going to divide that by 0.25, it got cut off, but it's supposed to be 0.250 liters. Because remember, this this equation here has to be in units of liters. So we had 250 milliliters. You do have to convert that to liters. And when you do that, you see here when you do the math that it equals 1 mole. Or 1 molarity, I should say. All right, so basically this is a simplified version of all the math that we are about to do in this session. Okay, let's turn our page. Now we're going to do the problem 4.11 on page 146. So why don't you turn to that page in your textbook, and we're going to do it together. The question is, calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 mils of solution. And so when you see this, right away, I like to put down the formula weight of sodium sulfate, so I figured it to be 142 AMU. All right, so let's look over what the book says we should do step by step. The first thing we're given is the number of grams of solute, 23.4 grams. So let's highlight that. We're given 23.4 grams of sodium sulfate and enough water to form 125 mils of solution. Its chemical formula, sodium sulfate, and the volume of the solution, 125 mils, we're asked to calculate molarity of the solution. We calculate the molarity using equation 4.33. And that equation looks like this. Let's rewrite it. Molarity equals moles of solute over volume of solution in liters. Okay, so we have to convert the number of grams of solute to moles and the volume of solution from milliliters to liters. Okay, so the first thing we want to do is convert the number of grams of solute. So here's our solute, sodium sulfate, convert that to moles. And the way that we convert it to moles is we do dimensional analysis, and we write down 23.4 grams of the solute, and we set up a conversion factor, and we know that the formula weight for sodium sulfate is 142. Okay, so opposite sides cancel. We eliminated grams, and now we are we have converted to moles. So when we do the math, we see that this works out to 0.165 moles of sodium sulfate. Now, you have to convert the volume of the solution, which was given to you as 125 milliliters. Don't forget, because the equation calls for you to the solution has to be in liters. So you want to convert that to the milliliters to liters. So you're going to want to just, put that off to the side. It's 0.125 liters of solution. Okay, so now we have all of our values. We have our moles of solute, right? Moles of solute. And now we have our volume. And when we have two of the factors here, we can now do the math to solve for molarity. So molarity in this situation equals the moles of solute, 0.165 moles, which I recommend not to drop any units or even write out the solute, because on these tests it asks to show all of your work. So I would not drop any of this. And you're going to put that over 0.125 liters, because again, I can't emphasize enough that it must be converted to liters of solution. And when you do the math, you come out with 1.32 moles, or molarity. The molarity. Okay, so now we did that math problem. Let's move on to C. Expressing the concentration of an electrolyte, which is an ionic compound. All right, so now we're going to talk about expressing the concentration of an electrolyte. And we remember that electrolytes are always ionic compounds, sometimes acids and bases. Okay, so that's what we're working on now, how to express the concentration of an electrolyte. All right, number one. When an ionic compound dissolves, the relative concentrations of the ions introduced into the solution depend on the chemical formula of the compound. For example, if you have a 1 molarity, don't call it moles. There's the temptation there to say 1 mole. It's molarity, which is totally different than a mole. So, for example, we have 1 molarity of solution of sodium chloride is 1 molarity of sodium ions and 1 molarity of chloride ions. Similarly, a 1 molarity solution of sodium sulfate is 2 molarity sodium ions and 1 molarity sulfate ions. 2 here because the subscript is 2 connected to sodium, and 1 molarity here because the sulfate ion, there's only 1. Therefore, the concentration of an electrolyte solution can be specified either in terms of the compound used to make the solution, which is 1 molarity sodium sulfate, or in terms of the ions that the solution contains. So it can be specified either way. Concentration, this is very important, can be specified either in terms of the whole compound or in terms of the ions. You could say 2 molarity of sodium ions or 1 molarity of sulfate ions. I hope that makes sense. You might want to read that over. Take a minute to read it, because when you're dealing with an electrolyte solution, terms can be specified in 2 different ways, and you need to understand the difference. Okay, so now what we're going to do is sample exercise 4.12 on page 147. And it says here, what are the molar concentrations of each of the ions present in a 0.02 molarity aqueous solution of calcium nitrate? All right, so I hope that you're opened up to that page. And I'm going to try to get it under here so that you could see. Okay, so it says here, we're given the concentration of the ionic compound used to make the solution and asked to determine the concentration of the ions in the solution. We can use the subscripts in the chemical formula of the compound to determine the relative concentration of the ions. So calcium nitrate is composed of calcium ions. Calcium has a 2+ charge, and a nitrate ion that has a 1- charge. So its chemical formula is CaNO3 in parentheses and then a subscript 2, because calcium has a 2+ charge. Because there are 2 nitrate ions for each calcium ion in the compound, each mole of calcium nitrate that dissolves dissociates into 1 mole of calcium with a 2+ charge and 2 moles of nitrate ion. Thus, a solution that is 0.025 molarity in calcium nitrate is 0.025 molarity in the calcium ion and 2 times that for the nitrate ion. So the nitrate would be 0.05 molarity. So I hope that you understand. You might want to do the practice exercise. What is the molar concentration of potassium ions in a 0.015 molarity solution of potassium carbonate? Well, we know potassium has a charge of a +1. They're asking for the molar concentration of the potassium ion, and the molarity is 0.015 molarity, and we're dealing with a compound of potassium carbonate. Potassium has a 1+ charge, but carbonate has a 2-, and you need this fan, and that's how you would have known that the carbonate is a 2-. And then the carbonate, we're just going to add it, is a 2- carbonate. Okay, so that means that the formula is K2CO3, and the concentration of the potassium ion is twice that of the carbonate. Therefore, as the subscript 2 after the K in the formula suggests that it should be, the concentration is going to be 2 times that, so 0.030 molarity for the potassium ion. Yeah, 0.03. Okay. Now we're going to turn the page, and we're going to do interconverting molarity, moles, and volume. This is on page 147 in your textbook. The definition of molarity, we have to continue to drill this into our long-term memory. The definition of molarity equals the moles of solute divided by the volume of solution in liters. I want to write that out, liters. Now, the definition contains 3 quantities. Let's look at it. The first quantity is molarity. The second quantity is moles of solute, and the third is liters of solution. Molarity is a conversion factor between volume of solution and moles of solute. So, for example, if you calculate the number of moles of HNO3 in 2 liters of 0.2 molarity of HNO3 solution. So figure out what you're given. You're given your liters and you're given the molarity. So now all you have to do is solve for moles. It's just plug and play. So moles, how do you solve for moles? Moles is equal to molarity times volume of solution in liters. So the molarity is 0.2 HNO3. And you're timesing that by the volume, which is in liters, and we don't have to convert it because it's already given to us in liters, 2 liters of solution. And when you do the math, 2 times 0.2 equals 0.4 moles. HNO3. So when you get done writing this problem out here, it's really important to make note that you can use dimensional analysis when you express molarity. So molarity is, the conversion factors is, you can write it volume of solution in liters over moles of solute, or moles of solute over the volume of solution in liters. So keep that in mind when you're expressing molarity. So the way that you could write that out is, let's just do it down here. Molarity is, you could do it liter, volume of solution in liters, over moles of solute, is equal to molarity. Okay, molarity, write that out. Okay, so this is our conversion factor. It could be written this way, or it can be written vice versa. You could put moles of solute over the volume of solution in liters. All right, so now let's do this. Calculate the volume of 0.30 molarity of HNO3 solution required to supply 2 moles of HNO3. So with dimensional analysis, you're going to start with what you know. You have 2 moles of HNO3, and you are, what's your unknown is your volume in liters. So dimensional analysis is you're going to cancel moles, and you're going to, so you're going to put 0.30 moles of HNO3 in the denominator, opposite sides cancel, and then you're going to put 1 liter, because this is our conversion factor that we just did down here. It's liters over moles of solute. You're going to put that liters in the numerator. Now you convert it to liters, and when you do the math, 2 divided by 0.3 is 6.7 liters of solution. So now you're going to do sample exercise 4.13 on page 148. They want to know how many grams, your grams of sodium sulfate is required to make, this is your unknown. Okay, so figure out what your unknown is in the problem. Unknown is grams of sodium sulfate. So to get to grams, you're going to have to solve for moles of sodium sulfate. And how many grams are required to make, here's your known. What you know is that you have 0.350 liters of solution, and you have a 0.500 molarity of sodium sulfate. So you're going to set it up. M, the molarity of sodium sulfate is equal to the moles of sodium sulfate over the liters in solution. And you start with liters, 0.350 liters, and you want to find moles because that's your unknown. So you set up your dimensional analysis, and you put liters in the bottom, 1 liter of solution, and you put 0.500 moles of sodium sulfate. Opposite sides cancel. You solve for your moles, which is 0.175 moles of sodium sulfate, and then you need to get the formula weight of sodium sulfate, which is 142 grams, and you times 0.175 moles times 142 grams, and then you get 24.9 grams of sodium sulfate. That's your answer. Okay, look that over and work on a practice exercise right underneath of it to make sure that you really understand the concept. All right, so that finishes off the notes, and now you need to open up to 4.5 worksheet, and we're going to go over the worksheet together real quick. Concentration. What does the word concentration mean? Concentration means a concentrated solution contains a large amount of solute per liter of solution. For example, strong coffee. So this would be strong coffee. It contains a large amount of solute. A dilute solution contains a small amount of solute per liter of solution. For example, weak coffee. This is your dilute solution. Now, you have to calculate the molarity of a compound or an electrolyte in a solution. One way we express the concentration, you're going to want to write this in here, of a solute is molarity. The symbol for molarity is a capital M. Molarity, the formula is capital M, moles of solute over volume of solution. And that's always in, remember what I said, always in liters. Now, how would you, the first problem is, how would you create, let me turn this over. How would you create 1 liter of a 1 molar solution for the compounds in the box? So 1 liter solution, you would get 134.45 grams of copper chloride, and you would add 1 liter of water. Okay, so you have to understand how would you create a 1 liter of a 1 molarity solution for these compounds. So you would get 134.45 grams of copper sulfate, and then you would add 1 liter of water. And for the hydrated copper chloride, you would put in 170.48 grams of copper chloride, hydrate it, and add 1 liter of water. Okay, that's how you would do that. How would you create a, cross this out, 0.100 liter of a 1 molarity solution for the compounds in the box? So you would do 1.100 moles of copper chloride, and you would set up your conversion factor, and you would put 1 mole of copper chloride in the denominator, opposite sides cancel, and you would put 134.45 grams of copper chloride in the numerator, and you would get 13.445 grams. And then you would, once you get that, then you would add 0.1 liter of water. Okay, so it's sort of like what we did at the top, except we had to answer the question with 1 liter solution, but this actually is 0.1 liter of solution. So in order to do that 0.1 liter of solution, we had to do 0.1 moles and then times it by the formula weight of copper chloride. And then we get the grams here of copper chloride, and then we add, I should write it here, and add 0.1 liters of water. Okay, now how would we do this for copper chloride hydrated? So it would be 0.100 moles of copper chloride over 1. And then we put it over 1 mole of all of that copper chloride hydrated over the molecular weight, 170.48 grams. And opposite sides cancel. And so we're left with, let's see, the answer is 17.05 grams. And then we're going to add 0.1 liter of water. Alright, if these two questions are a little bit challenging for you, I wanted to have you take out a piece of loose leaf so that we could work this through in baby steps. And again, the easy part about this 4.5 section of the chapter is that we are constantly manipulating this equation. Molarity equals, which is a capital M, the moles of solute over the volume of solution. So write this out just so that it helps you to, it keeps reinforcing this formula, because this whole section is about manipulating this formula. And so how did I get all of this? How would you create 1 liter of a 1 molarity solution? All right, so basically I'm just going to plug that into the equation. So if I have 1 molarity is equal to, and they didn't give me the moles of solute, but they did give me the liter. And if I solve for x, 1 molarity times 1 liter, because remember molarity's units are moles of solute over the volume. Okay, so that would, when you do that math, the liters cancel, volume and liters cancel, and then you're left with moles of solute. And the answer is 1. So it's 1 mole of copper chloride. Copper chloride. And if you look at this, the copper chloride, is equal to 134.45 grams over 1 mole. Or you could write that out as 1 mole equals 134.45 grams. So, in order to make a 1 liter of a 1 molarity solution for the compound, you would need 1 mole of copper chloride, and you would have to weigh it. So if 1 mole equals 134.45 grams, you would need 134.45 grams of copper chloride, and then you would add 1 liter of water, because remember, the liter is the solution, so you would add water to the copper chloride. All right, now let's look at this. How would you create 0.1 liters of a 1 mole solution for the compounds in the box? And remember that we're dealing with the equation where we have moles, 1 molarity is equal to, we don't know the moles, over 0.1 liter. So if you do the math, so let's put that on the paper. So we do 1 molarity is equal to X moles over 0.1 liter solution. We get 1 molarity times 0.1 liter. That's going to give us the moles, and it comes out to be 0.1 moles of copper chloride. So now we have to go back to our conversion factor, and we had to figure out how to convert that to grams, because we need to know how many grams of copper chloride we need to add to the water. So you do 0.1 moles of copper chloride, and then you use your conversion factor, because you know that 1 mole of copper chloride is equal to 134.45 grams, or you could write it 1 mole over 134.45 grams, or 134.45 grams over 1 mole. Okay, there's a lot of ways that you can look at this. So we're going to pick the one where the moles are in the denominator, 1 mole of copper chloride, and we're going to put 134.45 grams of copper chloride. Opposite sides cancel, and that's where we get 13.445 grams of copper chloride that we would have to measure out and then add 0.1 liter of water. So I wanted to go over that one more time in case when I did it the first time it wasn't as clear. I hope that makes a little bit more sense. Okay, so the next part is we're going to calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So right away we want to turn that to liters, 0.125 liters of solution, because remember the equation requires it to be put into liters. So we have grams, but the equation, always keep the equation in front of you. Molarity is equal to the moles of solute over the volume of solution in liters. So if they're giving it to you in grams, then you're going to have to convert it to moles. And the formula weight for sodium sulfate is 142 grams. So step number 1, convert 23.4 grams of sodium sulfate over 1 to moles. So we're going to put 142 grams here. Opposite sides cancel. We're going to put 1 mole here. And we get, if we do the math, 0.165 moles. And then if we use our liter, second step now, we're going to plug it into the equation to solve for molarity. So we have 0.165 moles of sodium sulfate over, remember, do it in liters, 0.125 liters of solution. Then we have figured out the molarity to be molarity equals 1.32 moles. That's our answer. Okay, so you should be able to do the practice exercise right here by yourself real quick. And then we're going to look at this. And I want you to remember before we answer this, where this is coming from. If you look back in your notes, remember expressing the concentration of an electrolyte, an ionic compound. You're going to want to read through all of this to remember that you can express in two terms concentration of an electrolyte. You can express it in terms of the compound, the total compound, or in terms of the compound's ions. So if the ions contain like a 2 subscript, then you're going to double up on the concentration. All right, so that's just a review from the notes. So let's do this. 1 molarity of sodium chloride is written like that, 1.0 capital M. In sodium ions and 1.0 molarity in chloride ions. 1 molarity solution of sodium sulfate is 2, because you have the little 2 subscript, molarity in sodium ions, and 1 molarity in sulfate ions. A 1 molarity solution of aluminum sulfate is 2 molarity in aluminum ions and a 3 molarity in sulfate ions. Now, the confusion can be here that you might want it. The temptation is, because it almost tricked me, because you see aluminum and then it has a 3+ charge, the confusion is that you might want to call this 3 molarity. However, you're not looking at the charge on the aluminum when you're making your decision. You're looking at the subscript next to aluminum in the compound. Okay, so the 2 is actually coming from, the 2 molarity is coming from the subscript 2, and then the 3 molarity for the sulfate is coming from the subscript 3. Okay, so make note of that so when you don't get confused during the test. What is the molar concentration of each ion present in a 0.025 molarity aqueous solution of calcium nitrate? Well, the first thing that you need to do is look up the charges, or you should know that the charge of calcium is a 2+ charge, and nitrate is a 1- charge. Again, because we have it here on the fan, nitrate is a 1- charge. Okay, so you're going to write that compound out, which would be CaNO3 2. And then you remember, you write this in, you can write the molarity in terms of the entire compound, and if you wanted to do that, it would be 0.025 molarity. But if you want to write it in terms of the ion, calcium will be 0.025 molarity, and nitrate will be double that. It'll be 0.05 molarity. All right, so that's kind of easy. You just can't let yourself be confused. And do not look at the charge on the ion when you're doing the math. You're actually looking at the subscript. And 2 is a subscript next to nitrate, and that's where you're doubling up. 2 times 0.025. Okay, now we're gonna have you could do by yourself the next practice exercise. And we're gonna you're gonna do this one by yourself. And then we're gonna go down to solve for molarity, moles, or volume, also converting between moles and grams. This is really easy. How many moles of HNO3 are present in 2 liters of 0.2 molarity HNO3? So your unknown, U for unknown, is moles. And your known, you have, is a volume. And the molarity you have also, which is a known, K for known, known, and you have an unknown. Now remember, we're dealing with this equation over and over and over again, so it's molarity equals moles of solute over volume of solution in liters. And we know, what we don't know is moles, so we have to rearrange the equation. And if you rearrange the equation, you have molarity times volume in liters equals moles of HNO3. And now you just plug it in. Molarity is 0.200 times 2 liters. And when you do that, you get 0.4 moles of HNO3. There you go. All right, let's quick turn page. What volume of 0.30 molarity would be required to supply a reaction with 2 moles of HNO3? So now our unknown is volume. Volume is the mysterious unknown, and we have molarity as a known, and we have moles as a known. So let's write that out again. Molarity is equal to, keep writing it, it reinforces it in your mind, moles of solute over the volume of solution in liters. And so we're going to plug this in, molarity, or I'm sorry, we can solve for volume. So volume is actually going to be molarity, or moles over molarity. It's going to be moles of solute over molarity if you were to solve for volume. And your moles of solute is 2. 2 moles of HNO3 divided by the molarity, which is 0.30 moles molarity. And when you do that, it turns out to be liters, because this is a conversion factor, and it would become liters. And when you do the math, you get 6.67 liters of HNO3. Okay, so this one you can do on your own. This one do on your own. And this is where we're going to end. Next time I'm going to talk about dilution.